Hello everyone. Today we're going to be talking about electric circuits, one of the most exciting applications of electricity that you'll learn about in this class. Now you might be wondering why I'm showing you images from a water park in an introduction to electric circuits. And that's because there's a particular ride that exists at most water parks that is exactly the same as an electric circuit in terms of how it behaves. Now I'm not talking about an epic water slide or a sick roller coaster with a big splash at the end. I'm talking about the type of ride that your parents or grandparents might really love. The greatest ride of all, the lazy river. Now, what does a lazy river do? Well, it's simple. It's basically just a big long loop, and there's a motor or a pump that pushes water in one continuous direction around the loop. So all you have to do is just sit in the tube and float. Because the pump is only pushing in one direction, the water can only flow one way. This is also true in an electric circuit when we talk about electrons all flowing in the same direction. Okay, so now that we've got our basic analogy, let's talk about actual electric circuits for a moment. Here I have a diagram of a wire. Now, if we want to recognize how electricity works, we have to remember that all matter is composed of protons, neutrons, and most importantly, electrons. Electrons are sitting inside of that wire right now, but they're not doing too much because they have no reason to do anything. As soon as I install a battery, however, the electrons will immediately begin to flow in the exact direction that I'm showing here, in this case clockwise, around the loop. Now, how do I know that electrons will flow clockwise in this case rather than counterclockwise? Well, that's because of the position of the two terminals of the battery. It's how I installed the battery that determines the electron flow. Here's what I'm talking about. On side A of the battery, and there's no significance to the letter A, I'm just going to have A and B for the two sides, we are looking at the negative terminal of the battery. That's the flat end. Negative terminal implies that this is the side of the battery that's made out of a metal that always has an overabundance of electrons. There's way too many electrons that cluster around this type of metal, and so the battery tries to get rid of them. The other side of the battery is called the positive terminal. That's the one with the little extra nub on the end. This is the side of a battery that's made out of a different type of metal. This particular metal loves electrons and never seems to get enough of them and loves to absorb them in. So you can probably tell why electrons would flow around in this circuit through the wire. It's because they're trying to get away from one terminal and they would love to get absorbed into the other terminal. You can also think of it as electrons, which are all negatively charged, repelling each other. And the wire allows them to disperse and become more spread out, which they like because they all have the same charge, and as we know, like charges repel. Now, the thing that this battery is doing for the circuit is it's providing something called voltage. That's the push that gets electrons moving. Voltage is actually kind of a complex concept, so we're going to simplify everything about voltage into this brief definition. Voltage is an electrical pressure difference between two locations or 2 points. The 2 points we're looking at in this diagram are points A and B, the two terminals of the battery. You can think of voltage almost like height. If you're describing the height of a person, you'd be talking about the difference between the bottom of their foot and the top of their head. And you can't really think about height without thinking of 2 points that you're comparing. Similarly, voltage is something you can only talk about if you are comparing two locations. It doesn't really make sense to say point B has a certain voltage or point A has a certain voltage. You can only say that voltage is blank between points A and B. So a battery is a source of voltage, and if you're curious how much voltage a typical AA battery gives out, it is 1.5 volts of voltage. So there's your unit of measurement for voltage. It is the volt. Now that we know about voltage, which gets the electrons moving in a circuit, let's go back to our lazy river analogy to talk about the next concept you need to know as you start to learn about circuits. If you take a look at all the people in these green tubes, as they float down the river, they're going to encounter some resistance and they'll probably bump into each other and the walls pretty soon. That's because if you look closely, you can tell that the river constricts a little bit and gets more narrow where this photograph is taken. So those people in the floaties will probably bump into each other, and that's going to cause them to slow down and stop flowing as quickly. So this is a concept that comes up in electric circuits as well when electrons bump into each other or bump into the walls of the container that they're in. This property is called resistance. What does resistance mean? Resistance is the opposition to the flow of electrons. Opposition means you are fighting against something. So if electrons want to flow and something is fighting against that flow, then it is in opposition to the flow, and it must be providing this thing called resistance. In the bottom right corner of the screen, I'm showing several different wires, from very thin to very thick. And in case you're curious, when wires get really, really thick, it actually becomes more convenient to use several small wires put together rather than one thick wire, because that makes the wire more flexible and you can bend it more easily. So you can ignore the fact that those are multiple small wires because that won't affect the question I'm about to ask. The question I want to ask is, out of all of these wires, which one do you think has the most resistance? Do you think you have the answer? How about the opposite question? Which of these wires has the least resistance? Pause the video, make your guesses, and then click play. Here's the answer. The highest resistance wire is going to be the skinniest wire. The lowest resistance wire is going to be the fattest one, the really thick wire. Why is this? Well, if you think about walking down a hallway, if the hallway is really crowded with other students and you only have a narrow passageway to get through, you're probably going to get slowed down. But if you're in a really wide open hallway where no one else is in it and you have lots of room to move around, then you're going to get to your next class as quickly as you need to. So, more narrow wires have higher resistance for electrons, and thicker wires have lower resistance for electrons. Okay, now that we know what the concept of resistance is, let's think about where you'll have to think about this concept as you construct and analyze electric circuits. The first thing you should know about resistance is that it's not going to be everywhere in high amounts. The resistance of a copper wire, and wires in our class will sometimes be called leads as well. You can think of how wires lead the electron from one place to another. The resistance of a copper wire or lead is usually small or negligible, meaning it's so little that you can ignore it. This means that electrons can get through copper wires very easily. That's because copper is an excellent conductor of electricity. You'll also notice that on the outside of a wire, we have an insulator of electricity, such as rubber or plastic. Okay, so if wires don't have a lot of resistance, what does? That would be devices, such as light bulbs, refrigerators, and hair dryers. These types of materials have lots of resistance in them, which means when electrons go into these objects, they have a really hard time pushing through the device. That difficulty that they have pushing through the device means energy is going to be released by that device. So let's talk about what that would look like for a simple object like a light bulb, which you're going to use a lot of in this class. Here's a question we could ask. What exactly makes a light bulb light up? Another way we could ask this is, what can be changed in order to make a light bulb become brighter or dimmer? Well, this is going to kind of relate to resistance, but it's also going to relate to the third and final concept you need to know about in order to study circuits. And that word you're going to need to know is current. We're going back briefly to our analogy of water rides to talk about whitewater rafting, where there's a very high current of water, where the water's moving really fast and everything's super exciting. So you could describe this as a high amount of current. Compare that to the lazy river we've been talking about, and you can see that the water's moving slower and things are way lower energy. So you could call this a low current of water. So now that we can refer to our background knowledge where we know that current means the speed at which the water is flowing, we can now apply that to circuitry. It turns out that the brightness of a bulb depends on the amount of current flowing in the circuit. Of course, we're no longer going to be talking about water, we're going to be talking about the current of electron flow. So here's how it works. When an electron enters a light bulb, you can see it's about to enter into that blue pathway, which is connected to the side of the base of the bulb. When the electron goes through that blue wire, it's going to travel up the blue wire, then it's going to go through a metal coil, we call that the filament of the bulb. That's made out of a special, highly resistive material that has lots of resistance, and that resistance causes the electron to scramble around, knocking into other electrons and banging into the walls of the coil. And that resistance causes heat to be emitted from the coil. That heat from friction activates some gases that are inside of the light bulb, and the gases are ignited, which creates the light from the light bulb. The electron then leaves that metal coil, that filament, and exits out the bottom of the bulb through that little green wire. So that's the journey of an electron through a light bulb. Now you can imagine if those electrons moved faster through that filament up at the top, you'd get more friction, more heat, and therefore more light. So let's establish this definition here. Current, in your class for when we study electricity, can be defined as the speed of the electrons as they flow through the circuit. Okay, now that we know about voltage, resistance, and current, we can start to put all of our information we've learned today together into a little summary here, because we're about to see how these ideas combine. Here's a summary of what we learned about voltage. Voltage is kind of like the push that makes electrons flow in the first place. Voltage is caused by a pressure difference between two locations or 2 points. And this difference can be forced into existence by a battery. You can also get voltage from other sources, such as static electricity or lightning strikes. After voltage, we learned about resistance, which we said is the opposition to electron flow. This is the thing that tries to get electrons to stop moving. What causes resistance? Resistance is caused by collisions with walls and other electrons. Finally, the third term we learned about today is current. Electrical current is the total speed or amount of electron flow. Now, you might have actually figured this out already, but electrical current is dependent on how much voltage and how much resistance there is in an electrical circuit. More voltage means more current. More resistance, however, means less current. So as voltage and resistance duke it out and fight each other, as they combine, we figure out how much current there's going to be. There's going to be an equation that relates all three of these terms. We'll talk about that in a second. It's important to recognize that electrical current is the most important property of them all. That's because the amount of current you have determines how much power your device is going to use, and, as they say, current kills. If your body is exposed to a high amount of current, that can cause damage to your cells and can even result in death. Voltage on its own doesn't hurt you, and resistance certainly doesn't hurt you, but current does. And so the way you get lower, safer currents is by making sure you have low, safe voltages, or by making sure you have very big resistances to fight against high voltages. Let's talk about how these things are all related, since I'm kind of getting into it anyways. Here is an equation that relates these three things to each other. The amount of electrical current that will exist in any circuit is equal to the amount of voltage that is pushing the electrons in your circuit, divided by the amount of resistance that is in your circuit as a result of things like light bulbs or refrigerators or other devices that put up resistance. This is an equation that you're probably not going to want to write when you're taking tests because it's so long and there's a lot of letters and spelling to remember. So I'm going to give you the shorter version of this equation and then we'll practice using it. This equation is commonly referred to as Ohm's Law. And you can probably figure out at this point in the year that Ohm was probably the last name of a scientist who discovered this relationship. And that'd be true. So let's shorten this equation to something more digestible. Let's use the letter I to represent current. And that's going to be the only weird one. Let's use the letter V to represent voltage. And let's use the letter R to represent resistance. So I equals V over R. That's Ohm's Law. The reason we don't use the letter C to represent current is because C already stands for the speed of light, or 3 times 10 to the 8 meters per second squared. It also refers to specific heat capacity, which is something you'll learn about in your thermal physics unit. For this reason, the letter I is used instead. You can remember that the letter I should be used for the current passing through a wire because the letter I actually looks like a wire, where electrons could pass upward or downward. So now that you know about Ohm's Law, let's talk about all the individual measurements. You've been introduced to them already, so let's just learn the units of measurement. First, voltage is measured in units of volts. You can shorten the unit volts to just the letter V. Resistance is measured in units called ohms. This also came from the scientist who discovered Ohm's Law. The symbol for ohms of resistance is the Greek letter omega. This is the most satisfying symbol in all of physics to write in your notebook. Try it out, it's a lot of fun. Finally, electrical current is measured in units called amperes. Ampere was also the last name of a scientist who contributed to our understanding of electricity, and so a unit was named after him as well. Amperes can be shortened to just the letter A. Alright, I think we're finally ready to take all of the knowledge we've gained today and try to solve 2 quick physics problems. Here's the first one. A 9-volt battery is powering a light bulb that has 30 ohms of resistance. How much current flows through the bulb? Feel free to pause the video right now and try to see if you can find the answer to this question along with the correct unit while showing full work with your pen or pencil. Go ahead and pause the video and try that now. Okay, now that I've given you a chance to try it for yourself, let's see if you got it right. The The question is asking how much current flows through the bulb, and they tell us the voltage and they tell us the resistance. So I'm pretty sure what equation I'm going to use. It's the only one we've talked about today, and it's Ohm's Law, which says current equals voltage over resistance. So if you were following along and doing this yourself, the first thing you hopefully did is wrote down the equation. Next step, plug in your values. The voltage was 9 volts, and the resistance was 30 ohms. 9 divided by 30 is 0.3, and the correct unit, since we're looking for current, would be amps of current, or amperes. That's actually something you'll notice in the next question, is sometimes we don't even use the full word amperes, we just say amps, because that's quicker. Okay, now on to our second problem. What is the resistance of a charging smartphone that requires 42 volts of voltage in order to maintain a current of 1.5 amps, or amperes? These are actually realistic numbers, and if your current in your smartphone got too high, your smartphone could actually break, and not enough current, and your smartphone wouldn't charge fast enough. So these are realistic numbers for what a phone would need to constantly feel in order to keep charging. They ask in this question, what is the resistance? And they give us voltage and they give us current. So once again, I know that this is the equation to use, but unlike in the last question, they didn't ask me for current. Instead, they asked me for resistance. Now that's a problem because right now, the way the equation is written, resistance is in the denominator. And that's no good because in algebra, you can't solve for something if it's in a denominator. Now I'm going to have to do 2 steps of algebra to rearrange the equation to solve for r, then I'll plug in my numbers, and then I'll get a final answer. If you think you can do that without me doing it first, feel free to pause the video, and then you can unpause it and see if you got it right. Okay, here I go. So the first step I'm going to do is get r out of the denominator because I need to solve for it. I'm going to accomplish that by multiplying by r on both sides of the equation. So now the left side is I times r, and the right side is v times r divided by r. It's pretty easy to see what I could do to clean this up. I can cancel out the r's on the top and bottom of the right-hand side, and now my equation has been cleaned up and it looks like this. I times r equals v. This is Ohm's Law, just like the one I had boxed out is also Ohm's Law. When you rearrange an equation, you've basically just made a new version of that equation that's more convenient for you. So it's handy to be able to do this and have the skill of rearranging formulas without plugging numbers in. That's actually a better thing to do than plugging numbers in right away. Okay, I need to do one more step because again, I'm trying to solve for resistance, and resistance is currently being multiplied by I. So what can I do here? Well, I can divide by I on both sides. That will allow me to get rid of the I on top and the I on the bottom on the left. Now, by cleaning up my equation, I can get that Ohm's Law can be written this way. R is equal to V over I. I've boxed this version out because it's the version I'm going to decide to use in this case. Now, if you were taking a test, you wouldn't have to show all of these steps. You would, though, have to show the original version of the equation that I gave you from a formula sheet, and then rearrange the equation in just one step if you want to, and show me the version you're going to use. You wouldn't need to show all those middle steps unless you want to, and it might be helpful to do so, but that's optional. Okay, plugging in my numbers now. R equals V over I, so V was equal to 42 volts, and I was equal to 1.5 amps. 42 divided by 1.5 equals 28, and the unit of measurement when you're solving for resistance is the ohm. So the answer to this question is the resistance of the smartphone must be 28 ohms of resistance. So that's it. That's Ohm's Law, and now you know about the 3 things that are in Ohm's Law: current, voltage, and resistance. I hope this was a helpful introduction to electrical circuits, and I wish you luck as you construct and analyze your own circuits very soon. See y'all in the next video.